So when we finished last time, we just barely got into this notion of what we call improper integrals. Now, improper integrals are any integral where there's an infinity involved. And infinity can be involved in a couple of different ways. It could be that you have a function which has some sort of an asymptote. So in other words, the function involves infinity, or the output, if you will. Or it could be that one of your bounds is at infinity, maybe positive infinity or negative infinity, or possibly both. And of course, there are functions where you have both things happening, both a vertical asymptote, but also a bound that involves infinity. So the question is how to deal with the infinite. And the answer is we're going to do approximations. And oftentimes, whenever we see a problem that involves infinity, what we want to do is we want to say, well, what happens as we get close? So what we're going to do is we're going to do our integrals the same as before, but we're going to just move away from where the infinity is. So maybe instead of going from 0 to 1, we say, well, some number b up to 1, if 0 is where the infinity is. And I can say, now that integral is perfectly safe. No infinity is involved. And I figure out what it is. And then I say, okay, now let b get closer and closer. And whenever you see the words closer and closer, that means it's a limit. So we ask what happens as we approach that trouble spot. And if it goes to a number, then that's what the integral is. And if it doesn't approach a number, then it doesn't converge. Now, it's possible that it doesn't converge, but it goes to infinity, or it goes to minus infinity, or it just might not converge at all. It just never goes to a fixed number. It just depends on the situation. Now, one of the things that we said is we said, if you have multiple problems, you really got to break it up into parts and handle each part separately. And that's the second point here. And that brings us to the example. So here we have this integral. Negative infinity to positive infinity. 2x over x squared plus 1. Now, the integral is not meant to be hard, because I think at this point in time, I'm hopeful if you see something like that, you know how to integrate it. Or at least you know how to take the antiderivative. What we want to do is we want to compute it in two reasonable ways, though one of them is more reasonable perhaps than the other. So part A. We're going to take the limit as b goes to infinity of negative b over b. So notice as b gets big, we're going from a large negative to a large positive. And so as we take the limit, we're definitely covering everything. Minus infinity to plus infinity. Okay, so let's see. This would be the limit as b goes to infinity of, well, what's the antiderivative of 2x over x squared plus 1? Natural log of what? Yeah, natural log of x squared plus 1. Then we're going to evaluate that from negative b to positive b. Okay. So what is this? Well, this is the limit as b goes to infinity of, plug in the top, log of b squared plus 1. So I'm just plugging in b for x, subtract, now I plug in negative b for x, and negative b squared, well, that's also b squared plus 1. Log of b squared plus 1 minus log of b squared plus 1. Is 0, because they're the same. So this is the limit as b goes to infinity of 0, which is 0. All right. Now at this point you're saying, of course, it makes sense that it should be 0. Because 2x over x squared plus 1 isn't just any normal function. It's mildly peculiar, mildly strange. Some people might say it's odd. It's an odd function. So when we have an odd function, and we have that symmetry kicking in, we should expect there to be cancellation. We should expect there to be 0. So it's like, okay, this totally makes sense. We're on board. No surprises. Now let's do part B. All right. Now, we would be very surprised if there was no surprise after doing part B, because there's been a big build-up here. Okay, so I'm going to predict we're not going to get 0. But let's think about what's happening here. We're still taking a limit as b goes to infinity, but now we're going from a large negative number to a even larger positive number. But as b gets big, I'm still covering everything. I'm still getting all the stuff covered. So you could really argue that justifiably, yes, this is going to get us from negative infinity to positive infinity, and life is good. So we do the same steps. It's the same function. So we still have the limit as b goes to infinity, log of b squared plus 1, evaluated from negative b to 2b. All right, well, that's the limit as b goes to infinity of log of, now we plug in 2b. Oh, whoops. Why did I put b there? Okay. Should have been x. Sorry. Got ahead of myself. Plug in 2b for x, and that would be 4b squared plus 1. Subtract, plug in negative b, log of b squared plus 1. All right. Now, these don't outright cancel. But what can we do? We have 2 logs. They're being subtracted. What are we allowed to do? Yeah, so this is one of the cool properties about logs, is that subtraction becomes division on the inside. So log of 4b squared plus 1 over b squared plus 1. And log is a nice continuous function, so I can pass the limit in. So log of the limit as b goes to infinity of 4b squared plus 1 over b squared plus 1. Now, what happens to 4b squared plus 1 over b squared plus 1? Goes to 4. You can see it by looking at the leading coefficients. As when you have polynomial, you look at the leading coefficients. That gives you the answer when the degrees are the same. And therefore, this is natural log of 4. All right. Now, if you compare these two, you might start thinking, ooh, that tells us that the natural log of 4 is 0. No, it's not. Natural log of 4 is definitely not 0. Okay, so what happened? Why is it that when we computed this integral from negative infinity to positive infinity in 2 different ways, we got 2 different answers? Shouldn't there only be a single answer? Any ideas?
We have a different leading coefficient on the upper bound.
We did, yes. But we're still computing the same area. We're still going from negative infinity to positive infinity. But yes, that certainly is what caused it. But why is it that when we're integrating the same thing, from negative infinity to positive infinity, we can get 2 different answers?
Maybe because the area of the curve, one's negative, the other is positive, so it ends up becoming 0 if you do that, but if you start with another direction, it's positive.
All right, someone has suggested, look, the area under the curve. One part's positive, one part's negative. And maybe it's the case if you extend. Things don't cancel out. In fact, that is what happens. See, what the case here is if you were to sketch this curve, it does something like that, where it tends to 0 as you head off to 0. And on the positive side, if you were to find this area, it's plus infinity. On the negative side, if you were to find that area, it's minus infinity. And so what we really have is that this integral, in some sense, is infinity minus infinity. Now, what do we know about infinity minus infinity? It's not 0. It's, I don't know. See, infinity minus infinity is one of these things we call indeterminates, which means it's ambiguous. There's not a good way to define it. And so whenever you see infinity minus infinity, that's usually a signal like, okay, watch out, be careful. Or there's a case of time to do more work. So this is why you have to break things up into parts, because it's possible that depending upon how you interpret the way to integrate it, if you don't break it into parts, you might get something interesting happening. All right. So let us go back to where we were a little while ago. This whole thing started when we said, let's look at the integral from negative 1 to 1 of 1 over x squared. Now let's go back and revisit this integral. We have better tools. or at least we have a better understanding of what to do. So positive 1 over x squared, we said, look, there's this asymptote involved, and so you're looking for something like such. All right. Well, our problem is at 0. So what we'll do is we'll say, let's break this up to split our problems, because we really have, in some sense, you could say, look, I have two problems. The problem as I approach 0 from below, and the problem as I approach 0 from above. So we should really think of this integral as negative 1 to 0 of 1 over x squared dx plus integral 0 to 1 of 1 over x squared dx. Because I want to separate that. Now, from here, what we can do is we can just pick one, and let's just, we can pick the first one. Say, all right, our problem is up at 0. 0 is where we're struggling. So we want to see what happens as we get closer to 0, but not quite at 0. So what we're going to do is we're going to say, what happens as we approach 0 of doing the integral from negative 1 to b of 1 over x squared dx. In fact, more precisely, we can just say we're approaching 0 from below, because it's a one-sided limit. Oftentimes this doesn't make a difference, but, we can be precise. The integral of 1 over x squared, I think we know that one. What's that integral turn out to be? Negative 1 over x. And another way to think of 1 over x squared is of x to negative 2 power. All right, so limit as b goes to 0 from below, we have minus 1 over x evaluated from minus 1 up to b, which becomes limit as b goes to 0 from below of minus 1 over b minus 1 over minus 1. Okay, so there's our limit. Well, we can clean up the last piece. That's really like minus 1 there. So the question is, what really is happening here is that we have a minus 1 over b, and then there's a minus 1 on the end. What happens to negative 1 over b as b goes to 0 from below? So remember, we say b is going to 0 from below, so that says b is currently a tiny negative number. What's true about negative 1 over b? It's positive, and it's also, if b is small, 1 over b is big. So it's a big positive number, and it gets bigger and bigger. The expression 1 over b gets bigger and bigger as b gets closer to 0. So that part heads towards infinity. Now, infinity minus 1, well, hard to recover from that infinity. So that says that this piece is really heading off to infinity. Now this piece, well, we could repeat the process, or we could say a couple of things. One thing we could say, look, there's symmetry. So whatever happens over here, it has to happen over there. Or we could just say, look, this is definitely positive. It can't be negative because the function doesn't go down. And if I have infinity, I can't counterbalance it and pull it down. So the moral is, if you put these pieces together, this integral is definitely going to be big. Infinite. Infinite. All right. Good. So the answer, turns out, was not negative 2. It was infinity. All right. Good to know. Let's try another one. Again, 1 over x squared. Where's our problem with this integral? The problem is at infinity. So this is one where now it's not the asymptote, the vertical asymptote, that's the problem. The problem is we go too far. All right. So our problem is at infinity. So we need to deal with that problem. Okay. So we're just going to get a little bit smaller than infinity. We pick a number close to infinity to start, like 2 or 3. Well, probably more you think like 100. But, 2 is just as close to infinity as 100 is. But okay, limit as b goes to infinity of integral 1 to b. See, we identified the problem, and now we're going to take a limit as we approach the problem. Now I'm thinking of b as a finite number, which means this is just another normal integral. All right. Now you might say, wait, which side do we approach infinity from? Well, there's really only one way to approach infinity, but if you really want to, you could throw on a one-sided limit. But all limits to infinity are one-sided. Okay, so we repeat the process. Now at this point, not much has changed from what we just did. It's the same antiderivative, and so it's negative 1 over x, evaluated from 1 up to b. So this is the limit as b goes to infinity of negative 1 over b minus 1 over 1, which means that's really a plus 1. And now we ask a similar question as we did before, but now it's a different phrasing. So now we have b getting really big. B is getting big, huge positive number, and bigger. What's happening to that minus 1 over b? Getting smaller and smaller, goes to 0. So this part is disappearing. And therefore, in the limit, we get 1. So this integral is 1. So it shows you that, yes, you can have integrals which involve infinity and get out a number. And that number has a meaning. It's a reasonable number. All right. Well, we're just going to do a bunch of these. We'll practice them. And the more we practice, the better we get. All right. Find the integral from negative infinity to positive infinity of 1 over z squared plus 1. Now in this case, this function has two issues, or rather this integral has two issues, because there's infinity in both bounds. All right, well, we can work with that. So what do we need to do? Well, one thing we can do is split it up into two integrals. So we split at a convenient point. Now, a convenient point from negative infinity to positive infinity is 0. It doesn't have to be 0. But I strongly encourage you, whenever you get a choice of where to pick something, pick 0. 0 is a great friend, an ally when it comes to doing mathematics, just because so many nice things happen with 0. So I can think of, all right, there's two problems, I break up into two integrals. But really, I can say, I know something about 1 over z squared plus 1. Now, this is not an odd function, but it is another type of function. Do you recall what this is? It's an even function. What does that mean? Well, an even function is one where there's nice symmetry across the y-axis. In other words, if you were to flip it over, you get the same thing. So we can reasonably say, look, by symmetry, if I know it's happening over here, I'll have the same thing happen on the other side. It has to be the same. In fact, the word symmetry, think of it, the sem means something like the same. Okay. So let's focus on this one. All right. So again, limit b goes to infinity, integral 0 to b, 1 over z squared plus 1 dz. What's the integral of 1 over z squared plus 1? Arctangent. Oh my gosh. This is one you should know. This one is near and dear to our hearts. It's such a beautiful antiderivative. It keeps us awake at night with joy, thinking about how beautiful the universe is, that it allows 1 over z squared plus 1 to have a nice antiderivative like arctangent. Okay, arctangent of z, 0 to b. All right, which means we're taking the limit as b goes to infinity of arctangent of b minus arctangent of 0. Now, what is arctangent of 0? It's 0. See, that's why one of the reasons I say, look, 0 is your friend. A lot of functions have a nice evaluation at 0. Almost all functions that we deal with evaluate to 0 or 1 when you plug it in at 0. So how do you know arc tangent of 0 is 0? Well, the question is, tangent of which angle would produce an output of 0? And the answer is tangent of a 0 angle produces 0. So that's why arc tangent of 0 is 0. Now we have this other question. We have arc tangent of b, but b is getting big. So we got to understand the arc tangent function, and it might help to recall tangent. So tangent looks something like this. Just at least a part of tangent does. And when I want to make the arc tangent function, what I imagine doing is I imagine taking the line y equals x and I flip it across. So that what happens is if this is the tangent, then when I flip across, I have something that looks akin to that. So this is arc tangent. These vertical asymptotes become horizontal asymptotes. Where are the vertical asymptotes of tangent? Well, 90 degrees, okay, but if we're in calculus, we say pi over 2. So pi over 2 is the top one. What's the bottom one? Negative pi over 2. So we know what the horizontal asymptote is for arc tangent. So in particular, as I head off to infinity, arc tangent does what? Goes to pi over 2. So this limit is pi over 2. Which means that if we take this integral, which is pi over 2, by symmetry, this integral is going to be the same. We put them together, what do we end up with? Pi. Which when you look at the function 1 over z squared plus 1, from negative infinity to positive infinity, it has nothing to do with pi. It looks like. That's amazing. That's cool. That's cool. All right. So here's another problem. Find the integral from negative 1 to positive 1 of x to the 2/3 dx. All right. Where's our problem at? At 0 again. In fact, you're probably thinking, hey, we did something really similar. That 1 over x squared is really similar. And if you were to sketch this function, which I can give you a quick sketch of it, it would look strikingly similar. You'd have a hard time distinguishing it when you got close. So we're going from negative 1 to positive 1. So it looks similar. It has a sort of a similar fill. All right. So, what do we do? Well, again, we have to break this up into parts. Now, in preparation, I will point out that the way we would normally write 1 over x to the 2/3 is x to the negative 2/3 power. That's our calculus way of writing that expression. Because when you're working with exponents, x to powers, it's nice to write it as x to a k. All right. So we repeat the process. Now we can save ourselves some work. We have symmetry. This is an even function. So we know that this will break up into two pieces, negative 1 to 0 of x to negative 2/3, and 0 to 1 of x to negative 2/3. So we just have to do one. They should both be the same by symmetry. So let's work on the second one. I want to do something a little bit different here. Because now the problem is on the lower bound. The moral is it doesn't matter whether it's an upper bound or lower bound, it's the same process. Now, I've been using b. You can still continue to use b here, or you can switch to any other symbol you want. It's just a placeholder. It's a name. So if you prefer, you could say, for instance, limit as a goes to 0 of the integral from a up to 1 of x negative 2/3 dx. Now, in our case, it's a one-sided limit. How are we approaching 0? Yeah, from the right. From the right, from the right. As we go to 0, we go from the right. Good. All right. So, now we proceed. What's the antiderivative of x to the negative 2/3? So yeah, you add 1 to the exponent, negative 2/3 plus 1 would be x to the 1/3 Then you divide by 1/3, which is the same as multiplying by the reciprocal, which means multiplying by 3. So 3x to the 1/3, and we're going to evaluate that from a up to 1. Whoops, too many parentheses. Okay. So this is equal to the limit, as a goes to 0 from above, of 3 times 1 to the 1/3, and the cubed root of 1 is 1. Good. Minus 3 times a to the 1/3. Well, 3 is 3. Nothing's going to happen with that. What happens to the cubed root of a as we approach 0? Cubed root of a goes to 0. So that part is okay. That means that we get 3. By symmetry, we're going to get the same thing on this side. So we end up getting 3 here, we end up getting 3 there, and so our answer is 6. All right. Oh, whoop, getting ahead of myself. There we go. Find the integral from 0 to infinity of x squared e to the x dx. Now, if we were to sketch x squared e to the x, we don't have to do a great job, but what happens to the function x squared e to the x? As x gets big, what happens to that function? Because we're heading towards infinity. See, there's our problem, is infinity. As we head off to infinity, what happens to x squared times e to the x? It gets huge. It's going to be massive. All right, so if we got a function which is getting bigger and bigger and bigger, and we're asking what happens to the area underneath it, what's the answer? Yeah, this one's infinity. That's no fun. Okay, so let's make it fun. Let's try x squared e to the minus x. Now what happens? All right, so previously you had like a big thing times a big thing. X squared times e to the x. Okay, huge, huge, huge. X squared times e to the minus x. See, x squared is still getting big, but e to the minus x is getting small. Which one wins? Do you know which one is bigger? Exponential function or polynomial? Exponential. Exponential wins the race. Exponential is always bigger than a polynomial. So that's, okay. So what does that mean? Well, that means that this function doesn't get bigger and bigger and bigger. What happens is we do start at 0 because you have that x squared. It gets bigger for a while, but then it's like, no. Exponential takes over and it heads back down. Now, just because it heads back down does not mean the total area is going to be finite. But it means that there's a chance. And that's what we want. We want a chance, because we want a chance to flex our mathematical muscles. All right, x squared e to the negative x. What is the correct tool to use to find the integral of x squared e to the negative x? Integration by parts. Now, what's the clue that it's integration by parts? Well, because, there's like 2 parts, right? There's the x squared part and the e to the negative x part. And there's not really a substitution. Remember, you always check for substitution first. That's your gold standard. You should always be thinking substitution, but there's not really a substitution that's clearly in play here. So let's just do some work on the side. So here's some side work. Let's just find the antiderivative. I'm not going to worry about the integral from 0 to infinity, because that's just going to sort of cloud things. All right, so u and dv, which part should be the part we differentiate? Which part should be the part we integrate? Which part do we differentiate? The x squared part, because if we differentiate that, that looks better. And the e to the negative x, if we integrate it, that looks about the same. So if you have something which doesn't change either under differentiation or integration, you say, what should you do with the other part? Okay, so we should hurry because we have so many more examples to do. du is 2x, v is minus e to the minus x, so you have u times v, so that's minus x squared e to the minus x, then minus the integral of v times du. So the integral of minus e to the minus x times 2x dx. Now you can clean this up. This is the same as minus x squared e to the minus x plus integral of 2x e to the minus x. So I'm just swapping the order here, and minus minus makes plus. Now we say, aha, we started with the integral of x squared e to the minus x. We've gone to the integral of x e to the minus x. How do we handle the integral of x e to the minus x? We integrate by parts. See, this is the nice thing. Integration by parts is a technique so nice, we get to do it twice. All right, so what do we do? All right, in this case, well, I'll switch colors here because we're doing our second iteration. We're going to let, again, once you commit, you got to stay committed. You know, it's not like dating. You know, calculus is serious. Once you're committed, you got to stay with it. So, what do? See, before we said the x squared part, that's the part that's u. So we got to stick with the part that really came from. So this is going to be our next u. So we have u equals 2x and e to the minus x. Okay, that's still our dv. dv e to the minus x dx. That says du is 2 dx. And v is minus e to the minus x. All right, so minus x squared e to the minus x plus, and since it's plus, I really don't need a parenthesis. I could put a parenthesis here, but it's plus, so I'm okay without it. Then we have u times v minus 2x e to the minus x is what that will become. And then minus the integral of v du. So that's minus the integral of minus e to the minus x, whoops, I'm almost off the side, times 2 dx. All right, so what do we have? We have minus x squared e to the minus x minus 2x e to the minus x. Minus minus makes a plus. I'll even pull out the 2. Integral of e to the minus x dx. But how do we integrate e to the minus x? Well, now what do we do? Yeah, we do it. It's like we're channeling our inner Nike. Just do it. Okay, right? Because it's an integral that we know. So minus 2 e to the minus x dx. Got ahead of myself, plus c. Okay, I want to clean this up a little bit. What do you notice about all our terms? All have e to the minus x. So we'll pull them out. And we'll pull it out, so we have what? Well, we have minus, they're all negative 2, x squared plus 2x plus 2. And then you have e to the minus x. But e to the minus x is the same thing as dividing by e to the x. All right, so there we go. There's our antiderivative. So, coming back to this problem, we take a limit as we head off to infinity, integral 0 to b, x squared e to the minus x dx, which is the limit. B goes to infinity of minus x squared plus 2x plus 2, all over e to the x, evaluated from 0 to b. Because remember, I don't need the plus c because I'm doing a definite integral. We evaluate. So that's our limit as b goes to infinity of minus b squared plus 2b plus 2 divided by e to the b. And now when I plug in 0, e to the 0 is 1. And then upstairs, what will I have? I'll have 2. And then there's a minus, and I'm subtracting that. So that makes a plus 2. And 2 doesn't change with b. So I'm going to head and pull that out of the limit. So I have this limit, and then there's 2. So now we have to figure out what happens to our limit. Well, we have a challenge. Upstairs, we have something getting big. Downstairs, we have something getting big. So it's like going to infinity over infinity. What do you do? Yeah. Le hôpital. It's back. All right? So if you have an infinity over infinity, we can pull out our tool. Okay. So here we go. All right. Apply le hôpital. Oh, le hôpital, mon ami, it's been too long. Oh, let's go get the baguette. Okay. Derivative of the top. What's the derivative of the top? 2b and 2. And downstairs, derivative of the downstairs. E to the b. And what happens to the plus 2? It's still plus 2 because it's outside of the limit. We're applying L'Hopital just to the limit part. The plus 2 is on the outside of our limit, so it's still there. All right. Now what's happening? Well, the upstairs is doing what? It's getting big, and the downstairs, it's also getting big. So what do we do? Oh, L'Hopital. Yes, exactly. Good. All right, so we apply it again. So we're going to take the limit. As b goes to infinity. Upstairs, what do we have? -2. Downstairs, e to the b. And the plus 2, it's still plus 2. Now what happens? Goes to 0. You see, notice the top. -2. It's not changing. That means it's game over, man. Game over. Whatever happens, happens. So you have a fixed number. Downstairs gets huge. That goes to 0. So our final answer is 2. That's it. All right. Good. Good. Now, this integral. Integral from 0 to 2 of 1 over the square root of 2x minus x squared. All right. What do we do? What do we do? Calculus has been suggested. Yes? We might do some calculus on this problem. Okay. So, if you saw this problem on an exam, what technique would you think to use? There's a square root involved, and you see plus or minus happening in a square root. What comes to mind? Trig substitution. You see a square root, you see plus or minus on the inside, you should think, hey, I should look for trig substitution. Now you should be aware sometimes we might just make a normal substitution, but on the upcoming exam, you should be pretty confident that something like just a normal substitution is not going to work. You got to be more creative. Now in order to apply trig substitution, you really need to have like a variable squared minus a number squared. The problem is that both these terms involve our variable. So we're not quite into the right form. So we want to work on rewriting this expression. Okay, so let's see. What could we do? Well, this is the same as 0 to 2, 1 over the square root. And I like, this is the highest power. So I'm going to say minus, then I have x squared minus 2x. And then I'm going to leave myself some space to think about this. I know I want a square. So I need to do something so that I can make this x squared minus 2x, rewrite it in the form that it is a square. I could complete the square, okay. If I were to complete the square, what would I need to do? What do I need to put to make that a nice square? So in other words, I want this to be a square. What needs to go in there? Yeah, there needs to be a plus 1. And I'm just going to close it up because I say that's my square. Now I have to be careful. I've changed my integral. Essentially, I've put a minus 1 down into the square root. I can't change. That's a different integral. I have to go back to the original. So how do I compensate? Put a plus 1 here. Now, for people who are like, whoa, you've put plus 2, remember there's a minus sign. So it's minus 1 and then plus 1. So it really is the same. The ones cancel out. Okay, so now if we rewrite this, this is the integral from 0 to 2 of 1 over the square root of 1 minus. I'll put this 1 in front because I like the minus being in the middle. And then this is a square, so it's x minus 1 squared. dx. Okay. Let's do a substitution, trig substitution. What's the right trig substitution to make here? So this is our x minus 1, that's our u. This 1 represents our a squared, which means that a is 1. So I have a squared minus u squared. Which form is this? Sine. All right. So we would choose x minus 1 equals sine theta. Dx would be cosine theta. And on a side note, the square root of 1 minus x minus 1 squared, what would that be? So it would be square root of 1 minus sine squared. It becomes cosine. Okay. All right. So let's see. We'll put this all together. Integral. We have 1 over cosine dx. Oops, I forgot my d theta there. Cosine theta d theta. And what are the bounds going to be? Well, we plug in x equals 0. We'll get 0 minus 1 equals sine theta. For what angle does sine theta equal negative 1? So at x equals 0, we want negative 1 equals sine theta. So if you think about your circle, sine is your y value, so negative 1 is down here. So it's negative pi over 2. At x equals 2, plug in 2, you get 1 equals sine theta. So what angle, well, that would be up here, that's where 1 equals sine theta. What angle gives you that? Pi over 2. Now, what happens next? Yeah, very subtle. We're going to come back to that and talk about that in a second. But it's the integral of d theta, which is theta from negative pi over 2 to positive pi over 2. And if we evaluate, what do we end up with? Pi over 2, subtract negative pi over 2, which is pi. Now at this point you're probably saying, Steve, you messed up. This was supposed to be something which was improper. Was this integral improper? If you sketch it, what does it look like? Looks like that. There's asymptotes at both 0 and 2, because if you plug in 0, you'll get 0 downstairs. If you plug in 2, you'll get 0 downstairs. Okay, so now you're worried about the answer. Is it really pi? It really is pi. I want to assure you it's pi. I'm not cheating you. This is not like, ha, I'm going to do it twice in one day. No. I'm not like, well, I'm kind of like that sometimes, but not today. All right. So where did we go? Well, here's the thing. You are blowing up at 0 and at 2, which is reflected in this 1 over cosine theta. Because if you plugged in negative pi over 2 and pi over 2, you'd have a 1 over 0. But it just so happened that after we did the substitution, that the improperness canceled out. So sometimes if you carry out a substitution, the part that's improper will go away. And you can get by without it. And to be honest with you, a lot of times when we do improper integrals, we're a little bit more relaxed. And we only pull out the limits when we're really concerned or if we don't know quite what's going on. All right, let me, in the last few minutes, I just want to talk about one other important idea. And this is going to be an idea that's going to be echoed later on in the course, which is about making comparisons. So there are integrals we cannot do. it's just hard. It's hard to do integration. But we can ask ourselves the question, does the integral converge? In other words, is it even a number? So sometimes we can answer that question. We may not be able to say what number it is, but we can say it is definitely some number. And once we know it's definitely some number, we can say, okay, we can approximate it up to some certain constraint. And the way we do it is we say, well, let's compare the thing that's really difficult to understand to something which is easy to understand, but we know the behavior. So suppose we have some functions, and we have f is below g is below h. And I'm going to assume that these are all non-negative. But all right, so f is below g is below h. And if that's true between a and b, then the integral from a to b of f is below the integral from a to b of g is below the integral from a to b of h, which makes sense. I'm saying if my function is smaller, my area should be smaller. That's okay. That's intuitive. How does that help us? Well, maybe we're saying, look, I want to show something diverges, but it's hard for me to figure out what the antiderivative is. I can say, look, if I want to show something diverges, if I can show something below it diverges, I also have to diverge. So, in other words, if something underneath me is arbitrarily large, I have to also be arbitrarily large. On the other hand, if I can bound something above, so maybe I want to say, does this converge? I can say, well, look, it's below something which converges. Then that says, look, I'm below something which can't be big. So I also can't be big. So that forces me to converge. So the idea is, I can bound things, and by bounding them, I can understand how big things can get. So a quick example, because we have time to do this. Actually, a quick pair of examples. Does the integral of 2 plus sine x over x converge? Now, what makes this integral hard? Probably the 2 plus sine x makes it hard. Well, let's think about 2 plus sine x. What's true about 2 plus sine of x? Can 2 plus sine x get arbitrarily large? How big can 2 plus sine x get? Well, sine x can get at most 1, so 2 plus sine x could be at most 3. What's the smallest it could be? So sine x smallest it could be is -1. 2 plus sine x smallest it could be is 1. So what does that say? Well, it says that 2 plus sine of x over x is certainly bigger than 1 over x. Okay? Now, the thing about 1 over x, that's a pretty easy thing to work with. The integral from 1 to infinity of 1 over x dx. Well, integral of 1 over x, natural log x, evaluated from 1 to infinity. Now we have to think about, okay, so here's where I'm saying you can be a little bit more lax in your notation. Of course, we don't plug in infinity. That doesn't make sense. So whenever we say, okay, 1 to infinity, what we really mean is what happens as we go to infinity. So log of 1 is 0, so that's not a problem. As you go to infinity, what happens to log of x? It goes to infinity. Log goes to infinity. Very slowly, it takes its time. It's the tortoise, but it gets there. Which says, all right, this has infinite area underneath. That's what we know about this function. And this is above something which has infinite area. So what's the conclusion about this as well? It also has infinite area. And now this other one, well, I'll just point out 2 plus sine x over x squared is below 3 over x squared, but we've already done 1 over x squared from 1 to infinity. This is finite. So what must be true about this part? It's also finite as well. All right. On to the next example. Well, actually, before we do the next example, I just want to make one more comment. This idea of making comparisons is going to be a really important idea. So really, I can't stress this enough. The last third of the class, we're going to spend a huge chunk of time trying to understand, is something finite or something infinite? And so the moral is, look, if you have something complicated, simplify it and try to understand what happens to that. And oftentimes, answering that can help give you insight to whether or not the hard, complicated thing works. So what you do is the reason we got rid of the sign x's, that was the complicated part. And I promise at the end of the semester, we're going to do this a lot. A lot. So we got to get good at it. So to help us, let's start with these integrals. All right. So we're going to do two problems which look very similar. For which values of p, so p is some number, don't know what it is, it could be arbitrary, does 1 to infinity of x to the p dx converge? Then we're going to ask the same question for 0 to 1 of x to the p dx. Now, if you look, these have different issues. Certainly, infinity is an issue here. All right. Now, what's an issue here? Well, you could have an issue here, maybe. And that will be an issue. So this will be a concern, is when p is going to be less than 0. When p is greater than 0, no problem. All right, so let's go through and think about it. So they're both going to be very similar, so we're going to do this, and then this one will almost be automatic. So we think about x to the p. Now the problem is that x to the p doesn't integrate in a single way. There really are two cases. So let's do the sort of obscure case first, which is p equals negative 1. So then that becomes the integral from 1 to infinity of 1 over x, because x to the negative 1 is 1 over x dx, which is the integral 1 to infinity, we just integrate, log of x from 1 to infinity. And again, when we write down an infinity here, or really any bound where some sort of problem is, when we say what happens at infinity, we don't really mean what happens at infinity. This is just code. And this is part right here, this is code for when you do that bound, make sure you think of it in terms of a limit. So what happens is you go to infinity. And we know that log tends to infinity, and therefore this part, at the upper bound we head to infinity, at the lower bound we head to 0, and so we get infinity. So note, converge does not allow for infinity. Converge means I want to go to a number. So negative 1 is out. Okay. What about p not negative 1? Well, 1 to infinity of x to the p. Now we can use our other rule, which is you add 1 to the exponent, divide by that new exponent, p plus 1, and you evaluate from 1 to infinity. Well, now let's be a little bit careful here. So I'll actually employ the limit just to be extra special, extra careful. p goes to infinity of x to the p plus 1 over p plus 1. Evaluate that 1 to b. So this is the limit as p goes to infinity of b to the power p plus 1 over p plus 1. And then subtract, when you plug in 1, it's finite, so I can put it outside of the limit, 1 over p plus 1. Okay. So now we think about what's happening. I have this number, because you got to be careful what's changing and what's not changing. So what's changing is the b. So this is the part which is moving around. And it's getting bigger and bigger. So the question is, all right, given that it's getting bigger and bigger, which power, p, is going to be good? See, if I have a number raised to a positive power, that's going to get larger and larger and larger. If I have a number raised to a negative power, it'll get larger and larger, but like 1 over a large number. So actually, the net effect is smaller. So what we see is that this limit here is 0 if the power p plus 1 is negative, and it's infinite if p plus 1 is positive. Or p plus 1 less than 0, is the same as saying p is below -1. And p plus 1 greater than 0 says p is above -1. So now we know what happens at -1. It's huge. We know what happens at -1 again. It's huge. And so what's our conclusion? Well, our conclusion is we want this power, p, to be less than -1. So the answer is this converges only when p is below -1. All right, so that's that answer. So that's the value of p. Now what about this other one? Well, the thing is we run through the same process. You say, okay, p equals -1, 0 to 1 of 1 over x dx. That's log of x from 0 to 1. Log of 1 is no problem. Log of 0, well, we say, what happens as you go to 0? And the answer is that as we go to 0, log of 0 blows up. Actually heads towards -infinity. So the result is infinity. So again, -1 loses out. And then if p is not -1, well, we have the same process here. So we're going to end up doing the following. So we have 0 to 1 x to p dx is going to be the limit, as now a goes to 0 from above, of x to the power p plus 1 over p plus 1. Evaluate that from a to 1, which is the limit as a goes to 0 from above of what? Well, plug in 1 over p plus 1 minus a to the p plus 1 over p plus 1. Now we have to ask ourselves a question. What happens? Well, okay, the 1 over p plus 1, because p isn't changing. P is a number. It's fixed. So I can think of this as 1 over p plus 1, pull it out, minus 1 over p plus 1, limit as a goes to 0 from above, of a to the power of p plus 1. Now a is a tiny number. So what's the case? What's the case here is that if I have a tiny number and I raise it to a positive exponent, right? So a tiny number to positive exponent, then that's going to go to 0. So this is going to go to 0 if the exponent is positive, or when we could say that p is above -1. Now, if the exponent is negative, it's like I have a very small number to a negative exponent, which means I have 1 divided by a small number. Well, that means it's blowing up. So it's infinity here. If we have that p plus 1 is negative, or p is below -1. So when does it converge? So the answer to this one, this converges when what? Well, not at -1, and not when I'm below -1, but only when we're above -1. So that's our when do we converge. It's kind of interesting to compare these two. See, this says, look, if you're going from 1 to infinity, you want the exponent to be below -1. If you're going from 0 to 1, you want the exponent to be above -1. And at both cases, -1, that's that dividing line. And we're going to see that that has really interesting behavior later on. So this is actually going to be important. We're going to use this in the third half of the course when we talk about when do things converge and diverge. So all right, so now we know about those integrals. All right, now let's do a little bit of a challenge problem. And I suspect this will challenge us. It'll stretch us a bit. 1 to infinity, 1 over x cubed plus 1. Now, without even doing anything, we can actually get an idea whether or not it converges or diverges, because, look, 1 over x cubed plus 1 is really more or less like 1 over x cubed for all intents and purposes. And 1 over x cubed, we would just, doing what we just did, will converge. So, okay. So, how do we approach it? Well, if we think about what we have, is we have a rational function. Polynomial upstairs, polynomial downstairs. So, the way you work with a rational function is you work on factoring. All right. Well, upstairs, by the way, we don't need to do long division because it's already lowest power possible upstairs. Now, here I have x cubed, which I can think of as x cubed plus 1 cubed. So it's a sum of cubes. And there's a nice little formula for a sum of cubes. So if I have a cubed plus b cubed, it's a plus b times a squared minus ab plus b. All right? There we go. There's our factoring. Now, a little side work here. We're going to write 1 divided by x plus 1 times x squared minus x plus 1 in the form as something over x plus 1. Because this is a linear term. X squared minus x plus 1, that's a quadratic term, and we'd have a hard time factoring that. And therefore, when we write it here, x squared minus x plus 1, I need a bx plus c. And we kind of expect that we should have three things we don't know, because we start with the cubic downstairs. So whatever this degree is downstairs, that's how many things we shouldn't know. We've got to figure out. All right. Clear our denominators. 1 equals a times x squared minus x plus 1 plus b times x plus c times x plus 1. Well, what can we do? Well, let's make good choices. So let's choose some nice numbers. How about x equals minus 1? All right. Well, if x equals minus 1, what do we get? We get 1. Here we get a. Then there's a minus 1 squared, which is plus 1. Minus 1 plus 1, and plus 1. So that's 3a. Then we get negative b plus c times 0. Oh, that's nice. So that says that a is 1/3. Well, any other good choices? 0 might be a good choice. See here how it's b times x? 0 is often, if nothing else, you always try 0. All right. Well, what happens there? We get 1 equals a times 1 minus 1 plus 1. So that's a. But wait a second. I know what a is. Okay, so I'm going to replace it. That's 1/3. Plus, here, 0 plus c, which is c, times 0 plus 1, which is 1. So that's plus c. Okay. So now I can solve for c. c is 2/3. Well, don't see any other good numbers to plug in, but I know a good number is always 1. 0 and 1, they're your friends. Use them. Hang out with them. Take them out to dinner sometimes. All right. What do we get? Plug in 1. 1 minus 1 plus 1. 1. That's nice. Okay, so that's again a, which is 1/3, plus b plus c. Okay, so b plus 2/3, and then here, 2. So we can subtract the 1/3. That would be 2/3 equals 2 times b plus 2/3. Divide by 2. 1/3 equals b plus 2/3. Subtract 2/3, and we end up coming to the conclusion that b equals minus 1/3. Nice. Okay, so what does that tell us? Well, 1 to infinity of a, which is 1/3 over x plus 1, plus b times x plus c. So b is minus 1/3 x, and then plus 2/3. Okay, that's b times x plus c all over x squared minus x plus 1. Okay, good. Well, for simplicity, we can go ahead. Everything has a third in it. Let's pull it out. 1/3 integral 1 to infinity 1 over x plus 1 plus. Now, let's start focusing on this second term. Here we have x squared minus x plus 1. Now, once we've got it down to irreducible quadratic, what you want to do is really write it in the form of a sum of squares. So it's like, okay, x squared minus x. What would we need to add to make it a square? Take the middle term, divide by 2, minus a half, square it, be plus 1/4. All right, that's now a nice square, and then it'll be plus, well, let's see, we have a 1/4, we need to get to 1, so that leaves us with 3/4 left over. And now remember, we pulled out a 1/3 out of everything, so upstairs we have a minus x and a plus 2. Okay, so let's note for a second, this is now a nice, perfect x minus 1/2 quantity squared. Now why do I mention that? Well, I want to make the upstairs look like things in terms of x minus a half. So for instance, I can think of this as minus x minus a half plus a half plus 2. I mean, that's certainly true. And if you rewrite that, that's the same as minus x minus a half, and then minus a half plus 2 is plus 3/2. Okay? All right. Now, that might not seem the most obvious thing to do, but we'll get there. We'll get there as to why we want to do it. All right. Over here. Why do we want to do it? Well, we really want to make this x minus a half match with whatever's upstairs, because we're going to head in that particular direction. All right. So where are we up to now? So we're now up to 1/3 integral 1 to infinity of 1 over x plus 1. And then we have plus, I'll write it as 3/2 minus x minus a half, all divided by x minus a half squared plus, and I want this to be also a square, square root of 3 over 2 squared. Good. Good. And dx. All right. Well, I think it's time for us to do a little bit of work on this side. So let's grab a piece of paper here, and let's work on this integral. How could we do that integral? Well, let's think of it as really, so I'm just going to do the indefinite integral for right now. So I'm going to have two parts to it. 3/2 over x minus 1/2 squared plus square root of 3/2 squared, and then minus, well, this will be its own integral, x minus a half over x minus a half squared plus square root of 3 over 2 squared. All right, so those are our two pieces. The second one is actually the easier one, because if you take u to be the denominator, x minus a half squared plus square root of 3/2 squared, well, du is 2 times x minus a half to the 1 dx. The second term drops out. Well, that's essentially what we have upstairs, just off by a factor of 2. So that's a half. So that says the second integral would become what? Well, it becomes 1/2 from here, du over u, or 1/2 natural log of this expression, x minus a half squared plus square root of 3/2 squared. Now, I suppose at this point, it might be easier to work with this going forward to say, yeah, this is still the same thing as x squared minus x plus 1. We'll come back to that in a second. And don't forget the minus sign. We're going to have to put that in there at some point. Okay. Now that's that integral. Let's talk about the first integral. The first integral is actually perfectly set up for trig substitution. Now you're probably thinking, there's no square root involved, but this is our a squared plus b squared form. It should remind you of arctangent, like x squared plus 1, because It is like arctangent. So if this is our u squared plus a squared, then the rule is u should equal a tangent theta. Well, in our case, that says that x minus a half is equal to square root of 3 over 2 times tangent theta. So what is dx? Well, dx is square root of 3 over 2 secant squared theta, d theta. And by design, what's going to happen downstairs? Well, what do we have? We have the 3 halves going upstairs. We have the dx, square root of 3 over 2 secant squared theta d theta. Downstairs, we're going to square that, which is going to give us our 3 over 4 times secant squared theta. Right, that's the x minus half squared. And then this, well, that's really still 3 over 4 plus 3 over 4. Whoops, sorry, I wrote secant squared. I got ahead of myself. That's a tangent. Oh my gosh, you can't even tell that's tangent anymore. All right, we've got advanced technology to make it look like tangent again. See? There you go. Now it looks like tangent again. Good, problem solved. You can pull out here the 3/4. Now if you gather everything, see you have a 3/4 and a 3/4 and 3 halves and a 2. You can do a lot of cancellation, and when you do that, you get what? The square root of 3 doesn't cancel, but all these other little fractions do. So the square root of 3. You have a secant squared theta. When you pull out the 3/4, you're left with tangent squared theta plus 1 downstairs. That's secant squared. And there's a secant squared already. Those cancel. So that's d theta. Which means we get square root of 3 theta. Now we go backwards. Well, what's theta? So theta, we solve for it. You take the square root of 3 over 2 across, so you get tangent of theta is equal to 2 divided by square root of 3 times x minus 1/2. So theta would be arctangent of 2 over square root of 3 times x minus 1/2. Like so. All right. So good. That's the first piece. That's the second piece. And now we have that last piece. So we're going to put it all together. And let's see what we have. So, don't forget about the 1/3. So 1/3. And now we're going to do what? 1 over x plus 1. Natural log x plus 1. Then this. But remember, we did that over here. So plus, we have a square root of 3. Arctangent. 2 over square root of 3 times x minus 1/2. And now we have a minus. Don't forget that minus. It's going to be important in just a moment. 1/2 log x squared minus x plus 1. Good. So that's the antiderivative. But we're not done because we need to evaluate 1 to infinity. Now let's put this aside. Okay. And we're going to need to work with this. So, we say, what can we do? Well, the problem here is what happens when we go to infinity. See, this part is going to be big on the inside of the log. So that's like heading to minus infinity. And this part, that's big inside the log too. That's heading to plus infinity. So it's infinity minus infinity. Now, infinity minus infinity doesn't mean the limit doesn't exist. It just means we got to do more work. And in particular, we got to use limits to figure it out. So this is a case where we really do have to use a limit. So we're going to take this to be 1/3 limit as b goes to infinity of this expression again. And this might be why the problem takes so long, as you keep having to write down stuff like this over and over again. All right, this expression, as we evaluate that from 1 to b. All right, so let's do our evaluation. We plug in b. So 1/3 limit b goes to infinity. of log of b plus 1. And I'm going to put the logs next to each other. So minus 1/2 log b squared minus b plus 1. And then plus square root of 3 arctangent of 2 over square root of 3 b minus 1/2. Okay, that's b. Subtract, because you got to also plug in the other bound, plug in 1. So we're going to get log of 1 plus 1, which is 2, plus square root of 3 arctangent of, and here we're going to get 2 over root 3 times 1 minus 1/2. We'll clean that up in a second. Minus 1/2 natural log 1 minus 1 plus 1. Okay. Whew. We finally have some good news. That's 0. Good. Good news for us. We have some other good news too. And I should say the 1/3 is also multiplying here. I'll go ahead and put the 1/3 so we don't forget. We have some other good news. 1 minus 1/2 is 1/2 times 2 means that those cancel. So this becomes 1 over root 3. And arctangent of 1 over root 3, that's actually something we know. That's pi over 6, a 30-degree angle. So this part cleans up relatively nicely. Relatively nicely. Now how about upstairs? Well, here we have this part is just getting big, because b gets bigger and bigger. If I subtract 1/2 from a big number, it's a big number. If I scale a big number by 2 over root 3, it's still a big number. So this is saying, what happens to arctangent in the long run? And the answer is, this part is going to infinity, so this part goes to the asymptote, which means this is going to pi over 2. Okay, so that part goes to pi over 2. That's well behaved. Now the logs. Here's where we say, what can we do? Well, we're going to use properties of logs. So we've mentioned some properties. Subtraction becomes division. The 1/2 comes in as an exponent. So first it becomes as an exponent. So let's think about this piece right here. So log of b plus 1 minus 1/2 log of b squared minus b plus 1. Think of it as log of b plus 1 minus, now I'm going to put this 1/2 power in, makes it a square root. So log of the square root of b squared minus b plus 1. So this is log of b plus 1 over the square root of b squared minus b plus 1. Now, b plus 1, I can write it as the square root of b plus 1 squared. b is positive, so there's no worries about square roots. So I really could write this as log of the square root of b squared plus 2b plus 1 over b squared minus b plus 1. And now we're ready to say, good news. This inside piece goes to 1. We can compare b squared over b squared. So it's like going to square root of 1, which is 1. Which means it's going to log of 1, which is 0. So this first term goes to 0. And now we've done the limit. Okay, so let's write down our answer. Here we go. We have the 1/3. What's left here? That goes away. Then we have square root of 3 times pi over 2. Okay, so that's that part. The 1/3, that's still there. So then minus natural log of 2. And then I have a square root of 3 times pi over 6. That's right there, that's square root of 3, that's pi over 6. And then again, the minus comes through. So minus square root of 3 times pi over 6. Now, there's not a lot we can do, but we can say, hey, there's square root of 3 and pi, so it's really like 1/2 minus a 6. 1/2 is 3 over 6. A 6 is 1 over 6. So if you subtract, that would be 1/3. So, what do we end up with it? Well, we have 1/3 times square root of 3 times pi times another 1/3. So pi square root of 3 over 9 minus 1/3 natural log of 2. And that's it. That's the answer. Just as you may have expected. Well, no. But the process, it works. And yes, it takes time, and got to be careful. I hope I'm right. But I'm right in the process. So if nothing else, we can learn the ideas. Factor, partial fractions, pull things apart. When you have this downstairs as something factored, rewrite your numerator in that form and integrate each part. Write it down your integral if you need to. If you have infinity minus infinity or infinity over infinity, throw in your limits. Figure out what happens in your limits. Be careful with your evaluation and simplify. And life is good. And that's sort of the big idea for improper integrals, which means we've had all our big ideas for integration. We'll do a little bit more practice and before our first exam. But for now, we're done. All right. Have a good day. Bye.